Good afternoon, everyone. First of all, I would like to thank the session chair and the organizers for giving me this opportunity to present our work. I'm Bhanu Bariyar from Techno India University, and today I'm going to present our research titled ASTriA Adaptive Semi-Supervised Trial Learning Approach for Scalable Malicious URL Detection. Let me begin with the motivation behind this work. Today, malicious URLs continue to be one of the primary entry points for cyber attacks, including phishing, malware distribution, credential theft, and online frauds. Every day, attackers generate thousands of new domains that remains active only for a short period. Because these URLs are constantly changing, traditional blacklist-based approaches struggle to detect zero-day attacks. Therefore, there is a strong need for intelligent detection systems that can generalize beyond previously unknown malicious URLs. Although machine learning has significantly improved malicious URL detection, one major challenge remains the limited availability of labeled data. Supervised models require large, accurately labeled datasets, but creating and maintaining these datasets is both expensive and time consuming. At the same time, cybersecurity system collects vast amounts of unlabeled URLs from threat feeds, web crawlers, and browser logs. However, most of these data remain unused because their labels are unknown. This creates a clear imbalance. Labeled data are scarce and costly, while unlabeled data are abundant but underutilized. This naturally raises the following research question. Can we effectively utilize these large unlabeled datasets to improve malicious URL detection while requiring only a small amount of labeled data? Answering this question forms the central objective of our research. Before proposing a solution, it is important to understand the limitations of existing approaches. Blacklists cannot detect previously unseen attacks. Deep learning models generally require high significant computational resources. Traditional supervised learning depends heavily on labeled datasets. Existing semi-supervised methods often suffer from noisy pseudo-label propagations. Once these incorrect labels enters a training set, they propagate through future iterations and gradually reduces model performance. Therefore, there is a still need for a scalable semi-supervised framework that can utilize unlabeled data while minimizing pseudo-label noise. This gap motivated the development of ASTriA. Based on these challenges, we defined four primary objectives of our work. First, we wanted to design a semi-supervised malicious URL detection framework that requires only a limited amount of labeled data. Second, we aim to leverage the vast quantity of unlabeled URLs through an adaptive trial learning strategy. Third, we want to reduce the dependency on expensive manual annotation while maintaining high detection accuracy. Finally, our objective was to develop a detection system that remains robust even as attackers continuously evolve their malicious infrastructure. In simple terms, our goal was to achieve high detection performance under realistic conditions where labeled data are scarce but unlabeled data are abundant. Our work makes five main contributions. First, we propose ASTriA adaptive trial learning framework. Second, we introduce consensus-based pseudo-label generation to reduce labeling errors. Third, we dynamically select the best performance-based classifier. Fourth, we incorporate a feedback refinement mechanism that continuously improves the model. Finally, our framework significantly improves malicious URL detection performance under scale-label conditions. These contributions together provide a scalable and practical framework for malicious URL detection. Previous malicious URL detection approaches can be broadly divided into traditional blacklist methods, classical machine learning, and deep learning approaches such as CNNs, BERT, and URLNet. Although each category has demonstrated promising results, they all have important limitations. Traditional methods fail against zero-day attacks. Machine learning requires labeled datasets. Deep learning models are computationally expensive and often difficult to interpret. Our proposed ASTriA framework addresses these limitations through consensus-based adaptive trial learning, which combines the advantage of multiple classifiers while reducing the risk of incorrect pseudo-label propagation. This brings us to important question: why semi-supervised learning? In cybersecurity, organizations collect massive volume of URLs from threat feeds, web crawlers, and network traffic, but manually labeling all of them is impractical. Semi-supervised learning addresses this challenge by combining a small labeled dataset with a much larger pool of unlabeled data. However, the quality of pseudo-labels is crucial. Therefore, ASTriA accepts pseudo-labels only when they satisfy consensus, confidence, and margin thresholds, ensuring reliable learning from unlabeled data. With this motivation, let me now introduce the proposed ASTriA framework. The framework consists of 6 interconnected stages that progressively improve malicious URL detection using both labeled and unlabeled data. It begins with dataset construction and feature engineering, followed by initial supervised learning on a small labeled dataset. The core of the framework is the adaptive try-learning stage, where three diverse classifiers collaboratively generate reliable pseudo-labels for unlabeled URLs. These predictions are the combined use of ensemble based on majority voting, while feedback refinement mechanism continuously improves the model by learning from difficult and low confidence samples. Unlike conventional supervised approaches, ASTriA continuously expands its knowledge using reliable unlabeled data, making the model more robust and adaptable over successive iterations. We evaluated ASTriA using the EntroURL-Bench dataset, which initially contained over 11,000 labeled URLs. Through one-hop backlink crawling, we expanded it to more than 41,000 URLs connected by over 2.5 million hyperlinks, providing a richer representation of the web ecosystem. Next, we performed feature engineering and applied a two-stage feature selection process using cross-validation ranking followed by recursive feature elimination. This resulted in a final set of 38 discriminated features, including lexical, entropy, trust, domain, and hyperlink-based features, enabling a comprehensive representation of malicious URL characteristics. After feature engineering, we trained the initial supervised models using only a small label dataset, that is approx 10% of the total dataset, which was divided into training and testing set using an 80-20 split. We evaluated 8 machine learning classifiers using standard metrics including accuracy, precision, recall, F1 score, and ROC-AUC curve. Based on their overall performance, the top performing models were selected as the base learners for the adaptive try-learning framework, ensuring both strong individual performance and effective ensemble learning. This slide presents the core idea behind ASTriA. Unlike traditional self-training, which relies only on a single classifier and is prone to noisy pseudo-labels, ASTriA employs 3 independent classifiers. A pseudo-label is accepted only when at least 2 classifiers agree and the prediction satisfies predefined confidence and margin thresholds. The accepted sample is then used to retrain the third classifier, preserving model diversity while minimizing label noise. By iteratively incorporating only reliable pseudo-labels, ASTriA effectively leverages unlabeled data and progressively improves detection performance. Initially, 3 selected classifiers are trained using the labeled dataset. Next, every unlabeled URL is passed through all 3 classifiers. Their predictions are then compared. If at least 2 classifiers agree on the same class, we evaluate both the confidence score and the prediction margin. Only predictions satisfying these conditions are converted into pseudo-labels. These newly labeled samples are added to training dataset and the corresponding classifier is retrained. This entire process repeats iteratively. The algorithm stops when no additional high confidence pseudo-label can be generated or when the maximum number of iterations has been reached. The important point here is that the learning process is adaptive. The model continuously improves itself without requiring additional manually labeled data. After the try-learning process converges, the predictions from all 3 classifiers are combined using majority voting, where the final class is determined by the agreement of at least 2 classifiers. This ensemble strategy reduces the impact of errors from any individual models and improves prediction stability. To further enhance performance, we incorporate a feedback refinement mechanism. Low confidence and misclassified samples are identified after each iteration and fed back into the training process. This allows the model to continuously refine its decision boundaries and improve robustness. Before applying semi-supervised learning, we evaluated the baseline performance of 8 supervised machine learning classifiers, among them random forest, gradient boosting, and decision tree consistently achieved the best result across accuracy, F1 score, and ROC-AUC. In contrast, linear models such as logistic regression and linear SVM showed comparatively low performance, reflecting the complex and non-linear structure of malicious URL patterns. Based on these results, the top performing tree-based models were selected as the best learners for our adaptive try-learning framework. This slide shows the impact of adaptive try-learning by comparing classifier performance before and after semi-supervised learning. As shown, all 3 selected classifiers demonstrate consistent improvements after incorporating reliable pseudo-labeled samples. For example, the ROC-AUC of random forest increased from 0.91 to 0.986, with similar improvement observed for gradient boosting and decision tree. More importantly, none of the classifiers experienced any performance degradation. This indicates that our consist-based pseudo-labeling strategy effectively controls label noise, allowing the framework to leverage unlabeled data while maintaining the stable and reliable performance. We also compared ASTriA with several state-of-art malicious URL detection methods. As shown here, ASTriA achieved the best overall performance, reaching 96.6% of accuracy and an ROC-AUC of 0.989 while maintaining high precision, recall, and F1 score. These results highlight the effectiveness and reliability of our framework for real-world malicious URL detection. Our experiments highlight four key findings. Adaptive try learning effectively utilizes unlabeled data. Consensus-based pseudo-labeling reduces label noise. Ensemble learning improves prediction stability, and feedback refinement continuously enhances model performance. Together, these components make ASTriA a robust, scalable framework for malicious URL detection under limited label settings. To summarize, ASTriA effectively utilizes large amount of unlabeled data through adaptive consensus-based try learning. The ensemble strategy improves the robustness while the feedback mechanism further refines the model. Experimental results consistently outperform existing approaches, and therefore ASTriA represents a practical and scalable framework for malicious URL detection under the limited label scenarios. Although ASTriA demonstrates promising performances, there are several exciting directions for future research. In future work, we plan to extend ASTriA using graph neural networks, trust propagation models, online learning techniques, and deep and dark web intelligence. We also aim to develop a real-time deployment framework suitable for operational cybersecurity systems. This brings me to the end of my presentation. Thank you very much for your attention. I sincerely appreciate your time, and I would be happy to answer any question or discuss any aspect of our work. Thank you.